All right, let's continue our discussion in this shaft. And right now we are going to do a sample problem in determining the shaft diameter based on the PMC, the Philippine Mechanical Code, and then the Philippine Agricultural Engineering Standards. Using the power rating tables from bias, and then we'll also use the equations provided by the ASME code. Okay, so let's read the problem. It says here, what would be the diameter of a line shaft to transmit 7.5 kilowatts if the shaft makes 150 RPM? So we have here the power and we have here the speed, right? So if we go to our lecture handouts, then you just have to select the shaft application, if it's a main power shafting, or if it is a line shaft that carries pulleys, or if it is a small short shafts or counter shafts. Then we just have to select these equations, and you would notice actually the difference is just this, right? This constants right here is just simply because of the I think this accounts for this difference in the allowable stresses. Okay, so actually this is, we can use it directly. Okay, so based on PMC, the diameter of the shaft is equal to the cube root of 1.1738 times 10 to the 6 times the power, right? And the power here should be in kilowatts, just take note of that, and divided by the speed in RPM. Okay, so let's label here, this should be in kilowatts and this one should be in RPM. Okay, so let's substitute all the values. So we have 1.1738 times 10 to the 6 times 7.5 kilowatts divided by the RPM, which is 150. Okay, so if you do the computation, what we'll get is 38.86 mm. And therefore, D should be, let's round up, so we can have D is equal to 40 mm. Right? Okay, the next is determine the diameter using the bias power rating tables. Right, so using bias tables, then okay, so using bias tables, what we need before we can enter this table is we need to specify first the required power, which is 7.5 kilowatts, and the speed is 150 RPM. Okay, so here's what we need, and now we go to table. Then of course we need to check if it is table table 3 or 4, and for table 3 it says line shaft, so that's fine. And here's our RPM, right? So it says we have 150 RPM, right? And we need 7.5 we need 7.5, right? .5 kilowatts, but the given is 7,152, right, and 11,357. And if it is 7,152, then that's 38 mm. If it is 11,000, then that's 44 mm. Okay, so we need 7,500 watts. So therefore, we need to do interpolations. Okay, so from table 3, we have the diameter and the power. So if it is 7,152 watts, this is in watts, and this one is in mm, right? So 7,152, this is 38 mm, and if the power is 7,500, right, watts, then this is what we want. Okay, and lastly here we have 11,357, and the diameter is 44. Okay, so if we have this values right here, then we can do interpolations. And let's write down by interpolation. Okay, by interpolation, the diameter is equal to 38.5 mm, right? And you can just simply therefore, or use d is equal to 40 mm. Okay, then you see that we can achieve actually the same value right here. Okay, and then now let's solve for the letter C. Okay, so assuming the shaft carries torsional loads and gradually applied loads, solve for the diameter using ASME code and use SY is equal to 41.5 MPa as allowable shear stress. Okay, so where did I get that 41.5? It's just simply based on these allowable stresses for line shafts, right? So the reason why I included this shaft carries torsional loads, because if there's bending loads, then of course we will the value or the computations would be different. So that's why it just says here carries torsional loads, and which means that the bending moment is negligible. Okay, and it says here gradually applied loads. Okay, so for when using ASME code, right, so we need to solve for the torque, right? So the torque is just or can be obtained from P is equal to 2 pi n T, and T is just simply P all over 2 pi n. So what is P? This is 7.5, right? 7.5 kilowatts times 1000, right? Because we need to convert that into watts, and 2 pi n, so n is 150 revolution per minute. Okay, times, right, we need also to convert this minute into seconds, because this one should be in Newton meters per second. Okay, so if you do the math, what we get is 477.46 Newton meter. Right, so the next is, now that we have this torque, then we can actually use the equation. Okay, so solving now for T. So the equation is 16 over SY pi, 1 minus P to the 4th, right, square root of Km times M plus alpha AD. Okay, so we need to solve for Km and K sub T. This shock loading factors. Right, so the shock loading factors, we have the nature of loading. This is rotating shafts. Also, we have a gradually applied or steady loads. Then our Km is 1.5 and our K sub T is 1.0. Right, 1.5 and K sub T is equal to 1.0. However, I have also mentioned in the last video that if we don't have actual loadings, then this term right here, this is just actually 0, and then this one right here, this is just 1 if we have a solid a round solid shaft, Right, so this simplifies to 16 over sy times pi. Actually, this is not just s sub y, but rather s sub y. So this is right s sub y. This is shear yield strength. Right. So this is not the strength in yield. I mean in tension, but rather this is a shear. Okay, and this is what else? And this is allowable. This should be allowable. Okay, so the equation simplifies to km, right, squared plus k t times t squared, right? And since we don't have the bending moments, then this is just 0. And therefore, our remaining equation is just simply 16 times sy times pi times k sub t times t. Right? So what is sy? Sy is this is, let's substitute the values. This is 41.5. This is megapascals times pi times 1.0 times the torque of 477 point what is this, 46 and 46 newton meters. Okay, so if you check the units, meters, millimeters, then just need to be consistent with the units, and what we get here is 38.84 mm, right? So again, d is equal to 40 mm. Okay, so I think that's pretty straightforward. And now let's do another sample problem regarding the critical speed. Okay, so our next problem says here a 2-inch shaft is supported by bearing which is 9 inch apart. The shaft carries no rating disc. I think this should be no rotating, right? Rotating disc, and its weight is 0.28 pound-force per inch cube. So this is a unit, not the unit weight, but rather I think this is a weight density. Okay, and its modulus of elasticity is 30,000, actually 30 times 10 to the 6 psi, and it has a uniform round cross section. And we are asked to find the critical speed. Okay, so just recall that in our equation for the critical speed, what we need is this equation is this g. We already know this is 9.81, right? For, of course, this one 4 meters per second squared, but in terms of English, this is 32.2 feet per I think this feet per second squared as well. Okay, and the problem just lies in finding this maximum deflection. Okay, so right here it just says that, or let's just write for now the given. So we have an L which is 90 inch, right? That's the length, and the modulus of elasticity is 30 times 10 to the 6 psi. And actually, in solving the deflection, we also need the moment of inertia. And for round solid shape, we have pi over 32 times d to the 4th, and we can just simplify it to, or let's just do that later. Okay, so here's our equation, and then the unit the weight density is 0.28 pound-force, right? Pound-force per inch cube, right? So that's the given data, and if we want to solve this, we can assume, or I mean, based from this equation, based from this problem, it says that supported by bearings 90 inch apart. So basically, it's something like a simply supported beam, right? So 90 inches in length. Okay, and of course, because of its own weight, then there's going to be deflection, right? And that deflection, we will find that using the tables. Okay, so here in our lecture handouts, we have here, we just need to check first the figure, if it is a simply supported, and if it's a concentrated loads, or if it is a uniformly distributed loads, right? So since we don't have any rotating disc, then that means that we don't have any concentrated forces, and we only have these uniform loadings from the weight, because what's given is this weight density. Okay, so that means that if we know the cross-sectional area, we multiply the cross-sectional area with this weight density, then we can find the distributed loadings. Okay, and from here we can see that the maximum deflection is given by this equation, right? Sigma delta max is just equal to 5 times the distributed loads L to the 4 divided by 384 EI. Okay, so that's the reason why we need this I value. Okay, so let's do that. Alright, so 5 times this distributed weight, right, or distributed loadings. So we can solve that using this weight density, 0.28 pound force divided by inch cube times the cross-sectional area. Okay, and the idea is that if here's our shaft, right, and here's our length, then if we have the 0.28 pound force per meter cube, then if we multiply this by the cross-sectional area, so that means that per meter, sorry, this should be squared, per meter, then that's gonna be the unit will be pound force divided by meter. All right, so that depends upon the length. So if we multiply this by the length, then we get the total force. Okay, but in terms of per meter, sorry, this should be feet, or what is this, inch cube, sorry about this. So inch cube, right, inch squared, and this one should be in inch, right? So let's do that. So pi times d squared all over 4, d squared all over 4, so that's our distributed loadings, times L to the 4 is 90 inch to the 4th, right? So this is our area, and here's our weight density. Okay, divided by 384 times, okay, 330 times 10 to the 6 psi, right? What else? Our value of I, which is 1/2 times pi, and what we get here is 0.0159 inch. Okay, so that's gonna be the deflection, and therefore we can now apply okay, solving now for the critical speed. Okay, so the critical speed is just simply the square root of the gravitational acceleration, acceleration due to gravity, and this maximum deflection, right? So this is 32.2 feet per second squared, and then this one is 0.0159 inch but of course we need to convert this inch to feet, right? So times 12 inch times is equal to 1 foot. Okay, and with that what we get is 155.66 1 over seconds. Actually this is radians per second, right? And if you want to convert this into the RPM, right? So this is just simply the critical speed in radians per second, right? Times 60 all over 2 pi. Okay, and what we get is 1486.45 RPM. All right, so it seems that the problem in solving this critical speed is just actually lies in finding the deflection. But once you have the deflection, then you can actually solve this critical speed and the rotational speed in RPM. All right. If you have a multiple mass systems, like if you have a rotating disc right here, then you just have to solve for the individual right here. So if we have a rotating disc right here, let's say we have three masses. So to solve this is first just imagine that this mass 2 and mass 3 is not occurring. Then what's gonna be the critical speed, right? So that's the meaning of these equations. So just imagine that this mass 2 and mass 3 they are not present, so that would be the critical speed for one disk. And then for the second disk, then just ignore this mass 1 and mass 3 and then solve for the critical speed, right? And then for the mass 3, just ignore this mass of 2 and mass 1 and mass 2 and then solve for the critical speed. And once you have all the three, then you can just use these Dunkerley equations to solve for the something like a total critical speeds. All right, so I think let's move on now to our next subtopic, which is the shaft keys. Right, so shaft keys. So shaft keys, they are actually something like an intermediate machine elements between the shaft and the hub. And when we say hub, it's just actually refers to the part of, let's say, the pulley or the sprockets or the gears. This portion right here, that's what we call a hub. It is where the shaft is being fitted, right? And in order to maintain the connection between this shaft and the hub or these sprockets or pulleys, then there must be some machine elements that will provide the transfer. The transfer of power, and also allows the rotation, because if this one rotates, then of course this will have some reactions and it will pass the reactions to this hub. Okay, so the application right here is shown in this figure. So we have an electric motor, and this is a pulley, and the electric motor has a shaft, of course, and in order to provide that proper connection is through the use of the key. Okay, so there are actually many types of keys, shaft keys, and the groove that's in the shaft and the hub, that's what we call the keyway. Okay, and by the way, in this figure there is another part right here. This is what we call the set screw, so it provides additional locking for this assembly. All right, so for based in our PAS 304, the key is defined as those elements which are used to prevent relative movement of rotating members in the shafts or spindles to which they are mounted. All right, so that's the the definition based from our PAS. So it is used to prevent relative movement of rotating shafts and of course provides powers. Okay, so as I've mentioned that there are actually many types of keys, and in our PAS 30, I think the list 304, it only presents three types of keys. So we have these parallel keys. Basically, from the word itself, the sides they are actually parallel, and further we can have a key that has both ends that's round. So here's an example. So it has a round end, or we can have both ends rectangular. So instead of being round, it's just being straight, or we can only have one end round. So one end is round and the other end is a straight or a square or rectangular. Okay, so that's one type of key, of shaft key, and the other one is what we call the tapered keys or taper keys. So from the name itself, basically it's just tapered. So instead of having straight, viewing from a side view, instead of having that straight dimensions, we have here something like that's a tapered dimensions. Okay, and we can have a gib head. So here's a gib head, or we can have a without gib, right? Without gib, and here's an example of with gib head. And another example is, or another type is the Woodruff keys. Basically, it's something like a semicircular cross section, and it is further classified as normal. In normal form or Whitney form. When we say normal form, it's just a semicircular shape, and for the Whitney, it has this chop off portion. So instead of having a full circle, full circumference right here, it has this chop portion right here. Okay, and another one is if you notice if you notice the connection. So if here's our shaft, here's our hub, then here's gonna be the keyway, right? So it's the same for these tapered keys, except for these Woodruff keys, they don't have this keyway all throughout the length, so only some portion right here. Okay, so that's one characteristics of these Woodruff keys. Okay, so as I've mentioned that we will only focus focus our computations in only one type of keys, and that's going to be the square keys. Okay, and before we delve into the equations, then I just would like to present to you the parts of this key and shaft assembly. Okay, so when we say diameter, that actually corresponds to the diameter of the shaft, and for the width of the key, we designate that as B, right? This is B, and for the height of the key, this is H. And therefore, if we will only consider a square key, then that means that B is equal to H for a square key, right? And the length of the keyway is we designate that as L. Okay, so usually in the design of a square key, this one, I mean, this cross section is already given or can be obtained directly, but what we need is how long it needs to or what length do we need in order to provide proper resistance in terms of shear or bending moments. Okay, so if we check this figure 13-8 right here, we have here the forces of the key. Forces acting on the key. So we can have either a shear force, right, or we can have a bending, not bending, but rather bearing stress or compressive stress. Okay, so here's our geometry right here. So you just have to read through this, but the equation that we will be needing is this one. So since we will consider the resistance in shear, right, and this one is the resistance in bearing stress, right? So the derivations is just actually taken from basic mechanics, and we just need to include some factor of safety if there are given, if it's given. I think here in our lecture handouts, it says here that the factor of safety is 1.5 for smooth load, or if you have a minor shock loadings, then that's 2 to 2.5, and if we have severe shock loadings, then the factor of safety can be up to 4.5. Okay, so again, when we say design of keyways, what we want is actually the length. How many lengths? How long would be the length required to resist the shearing forces or the bearing stresses? Okay, so right here, here's our figure of the relationship between the diameter of the shaft and the distances or the dimensions of the square keys, right? So if this is D, and if you use a square key, this is D over 4, so this is just 1/4 of D, and the height is also 1/4 of D because it's a square. And how deep the groove is just simply 1/2 of 1/4, which is 1/8. Okay, and in terms of design, the length. What's recommended is to have a length of should be less than or equal to 1.5 D. Okay, so what that means is, what if we need a length that's greater than 1.5 D? So that means that we can provide one key right here and another key in this in the opposite direction. And if it is still not enough, then we can use this. These configurations. Okay, so that's it. Okay, so I guess we will continue our discussion in the next video, and we will do computations regarding this key. So see you in the next video.